So a good way to start kind of exploring the PID algorithm is just to jump in and simulate stuff. So I've kind of put this script together from sources I found online. And so I guess just real quick I'll go through it. Right, these first lines are just kind of clearing our canvas. And then right here, these three lines, they're defining some transfer functions. So this is kind of math that I don't necessarily want to get into, but these are all in S domain functions, which has to do with taking the Laplace transforms. So here, this is just so we can have a symbolic representation of S for our S domain. And then here, you see we've got our Kp, Ki, and Kd. And so this is actually the S domain representation of our PID controller. So this is essentially the equivalent of our time domain, where we have Kp times air plus Ki times the integral of air plus Kd times the derivative of the air. So this is kind of the same thing, it's just MATLAB prefers to work with this S domain. And this is the transfer function of our plant, or what we're trying to control. And so this is actually using the TF function, and this is basically the numerator. This describes the numerator, and this describes the denominator. But once again, we don't really need to get into that. It's just kind of something that we've got to mess with. So these numbers are somewhat arbitrary. They're just kind of there to be a system that we can tune. And here's our parameters that we can tune. Right, Kp, Ki, and Kd. Right now I've got them initialized all to 0. And then here's where we're running our quote-unquote simulation, where we're kind of testing a feedback controller model, where this is our controller and our set point is 1. And we're doing a step. We're doing a step function, which is basically setting it up where we start at 0 and it instantly go up to 1. So that's describing our set point, and then it also generates a nice plot. So real quick, let's just run it and see what it looks like with our coefficients at 0. So no surprise, right? Our output doesn't do anything; it just stays there. So our step function, right? Our set point is at 1, so we want it to get up to 1. That's what we're trying to control to. But not surprisingly, nothing happened. So let's start tuning this. I recommend, starting with small increments, but for the sake of time, I kind of have a feel for what these values should be. So I'm just going to start at like 0.1, which is still a pretty small increment. So let's run that and see where that puts us. So here's our step response, and we see that we actually have some movement here. But the problem is that it only gets up to 0.2, and we're really trying to get to 1. So we don't, obviously it's not fully tuned yet. It got somewhere, but it didn't get where we need to go. And also it took 4 seconds to stabilize or get to that point. So let's kind of ramp this up here, and let's try 0.5 now and see where that puts us. So we got our proportional gain is at 0.5, and now we're getting higher, right? We're almost to 1. We're at 0.55 around, and it takes 2 seconds to get there. So let's test again. Maybe let's try 1 here. Let's see what we get. So now we're at 0.7. So that's getting closer. Let's go a little bit higher here. Let's try 1.5 and see where that puts us. So we didn't get that much of a gain here. We went from 0.7 to about 0.8. So maybe, usually when I start noticing very small gains, I usually roll back and just keep it there. So I'm going to keep it at a 1. And now I'm going to let this integral term kind of get us home. So let's just add a little bit. Let's just add 0.1 and see what that does for us. Just a little bit of integral gain. So check it out. We were able to get to 1, right? We're able to get to our set point. But what's the problem here? Well, it took 80 seconds to do. So the integral is having an effect, and that integral is slowly raising up our value until we get to 1. But that's just it. It's going really slowly. So let's actually let's kind of ramp this guy up and see what happens if we increase it a little bit. So there now, it's still getting to 1, and it took 12 seconds. So we're getting better, getting better. Let's try this at 1 and see what that does for us. As you can see, this tuning process, there's lots of ways you can go about it, but trial and error is a valid way to kind of tune some of these things. So this took 6 seconds. Let's bounce this up to 2 and see where that puts us. 1.8 seconds. That's not bad. And now this response time, that's something that you're going to want to design for. I mean, usually you want it to be as fast as possible, but that's not always achievable. And also something to consider is, let's say we put Ki to be a little bit higher. Eventually, you can have things tuned where you'll start getting this phenomenon called overshoot, where your set point is 1, but you actually are trying to get there so fast that you overshoot it, and then you kind of bounce around, and then this is called settling, right? It's settling on its value, and so it still only takes 1.8 seconds, but this is, for some systems, this might be undesirable. So let's just maybe, looks like 2 was a decent value there, right? So and this is a case where I think we're able to achieve getting to our set point without using our derivative gain, which is nice. The derivative, well, sometimes you need it, but if you can do things with this Kp or even Kp and Ki, that's usually preferable. So I would say this system looks pretty well tuned. And this system could be anything, right? It could be a heater controller, it could be motor speed, it could be lots of different things. But some systems are going to be more complex. Like a heater is actually a reasonably simple system, albeit it's really slow. It's pretty simple. But something like controlling the RPM of an engine, and you've got multiple factors, the transfer function for that, or the way it's controlled, it might be a lot more difficult. So we'll look at something with derivative term in the next video.